Hi all. Today we discuss section 14. In this section we first discuss two theorems together because if we prove 14.4, then we can consider theorem 14.1 as the special case of this theorem 14.4. So first we ultimately we prove theorem 14.4, rather proving these two theorems separately. So we start with the proof. This theorem 14.4 states that obviously I will explain the statement of theorem 14.4. If we have a subgroup H of a group G, then the left coset multiplication is well defined by the equation AH BH equal to ABH. That means if we consider a set of four distinct left cosets of H, then define a binary operation or an operation H BH is equal to ABH. So this is binary operation, or this is well defined in the collection of all distinct left cosets if and only if H is a normal subgroup. So first of all we need to observe the definition of normal subgroup. So normal subgroup, the definition of normal subgroup is, suppose we have a subgroup, we have normal subgroup here, subgroup. Suppose we have H is a subgroup. Suppose we have a subgroup H of G, and we observe that H is equal to HA for all A belongs to G. Then this H is said to be normal subgroup. H is normal subgroup. That is, this is the definition of normal subgroup. So for any subgroup H, its left cosets coincides with the corresponding right cosets. That is, every left coset coincides with corresponding right coset. Then that subgroup can be considered as a normal subgroup. So if you consider the kernel of a homomorphism, then we have already observed that if H is a kernel phi, then we have observed that H that is equal to phi inverse of set of phi of A, that is also equal to HA. So if you already observed this in the previous section, so we can easily get this H as the kernel of a homomorphism is normal subgroup. So this normal subgroup or this kernel has this property, H at HBH is equal to ABH as a well defined operation in the set of all distinct left cosets of kernel. So once you observe this theorem, then we can easily conclude that 14.1 holds, because in 14.1 it states the properties of the kernel of the homomorphism. So first we prove the theorem 14.4 by assuming that H is a subgroup or the characterization of the normal subgroup. So H is a normal subgroup if and only if AHBH is equal to ABH. So we start with the first assumption. H suppose that H is a normal subgroup. H is a normal subgroup means we have AH equal to HA for A belongs to G. Then we need to prove that if we collect all the left cosets H, that A belongs to G, this is a set of all distinct left cosets, we call this as S. We show that this operation H star BH equal to ABH is well defined. How will you prove that this is a well defined binary operation, or how will you prove that this is a binary operation? So in order to prove this is a binary operation, we usually if you have a function f from A to B, then how will you prove that f is a function, or how will you prove that f is defined? So if you take any a1 a2, from A, then we find f of a1 as well as f of a2. Then if you observe that these two are equal, then we can say that f is a function. Otherwise, what happens if this happens, f of a1 not equal to f of a2, then we can say that this is the common element. A has, if we put it as A, then A should have at least two images, so that doesn't satisfy the condition of a function or definition of the function. So in order to prove that a map is a function, we need to prove that we take two arbitrary elements from the domain, then find the images, and we'll prove that those are also same. So actually this is a binary operation. From binary operation can be considered as a map from S cross S to S. Okay, so R is a function from S cross S to S. So if we choose, this is in case this S cross S equal to A, the domain, if we choose two elements from the domain, then we need to choose two ordered pairs from S cross S. I choose A1H B1H as the first ordered pair and A2H comma B2H as the second ordered pair. And in order to prove f is a function, A1 equal to A2 implies. So here we need to prove that star is a function. Then if we choose two elements from S cross A, first element is the first ordered pair and second element is the second ordered pair. And if we assume these are equal, then we need to prove that is image. What is the image? Image is A1, image of A1H, B1H is A1 B1H. We need to prove that image of this ordered pair is same as image of this A2H, A2 B2H. So ultimately we need to prove this inclusion of sets. Okay, so first we try to prove that A1 B1H contained in A2 B2H. In the similar fashion, you can prove the other inclusion as well. A2 B2H is contained in A1 B1H. So our assumption is the equality of these two ordered pairs. Say if we have these two ordered pairs are same, then A1H should be same as A2H and B1H should be same as B2H. So how will you prove this equality? So we start an arbitrary element from the left side, say x from A1 B1H. We will prove that this x is an element of A2 B2H as well. So we start with x belongs to A1 B1H. So x takes the form A1 B1 some element of H, say H1. Okay, so we need to prove that this is same as element of A2 B2H. Okay, so we write this x as A1E, okay, and B1H. If we insert E, the identity element, so that that product will be, or that element will be the same. So if we consider A1E as A1H, so E is an element of capital H, then A1E is an element of A1H, then we our assumption is A1H is same as A2H. Okay, so we have, this is A1E can be written as A2 some, this is H1, and A2 some element H2, and we know that B1H is same as B2H, so we write this is B2 some B2 into some H3. Okay, so we know that we also assume that H is normal subgroup, so left coset coincides with right coset. That means this is an element of the right coset of H. Okay, right coset due to B2, so that is same as B2 into some H3. Okay, so A2 H3 can be written as well, and H2 B2 can be written as B2 H3. How will this possible? H2 B2 is an element of H B2, that is equal to B2H, because left coset coincides with right coset. So every element of the form HB2 can be written as B2 into some element of H. So H2 B2 can be written as B2 into some H3. Now this is an element of, this is H2B2 and H3, I'll put it as some H4. We already used H3, this is H4. So H4, H3 is again an element of H. Then this is an element of A2B2 capital H. So every element of A1B1H is an element of A2B2H. Similarly, you can prove that A2B2H is, every element of A2B2H is an element of A1B1H. So similar fashion, you can start with an element in A2B2H, then you can easily prove that X is a, or by following all these steps, you can prove that X belongs to A1B1H. That is, A1B1H is same as A2B2H, which shows that whenever these two ordered pairs are the same, then the corresponding images are also same. So this shows that star is a binary operation. So this is the one inclusion. Whenever H is a subgroup which is normal, then this operation AHBH is equal to ABH is also well defined, or that can be considered as the ordered can be considered as the binary operation on the set of all distinct left cosets of H in G. Okay, so next we have to prove the converse. So by assuming that H BH HBH equal to ABH, assume this, then assume HB is equal to ABH, then we need to prove that H is a normal subgroup. Okay, so every element of the left cosets of the H is in the corresponding right coset of the H. Okay, so that is to prove, we need to prove that H is normal. Okay, to prove H is normal. Okay, that is, H is normal means AH equal to HA for every A. So this is what we have to prove next. To prove this, we observe the assumption. What is the meaning of AHBH is equal to ABH? The meaning of this is, if you consider the product of two cosets AHBH, then we will get the coset containing AB. Okay, that means if we choose any element X from AH and Y from BH, then the meaning of this statement is, then XY is always an element of ABH. Okay, that means the product of any two elements of these cosets is in this ABH. That is the meaning of this. So by assuming this, we need to prove that AH equal to HA. Okay, so in order to prove AH equal to HA, we start an arbitrary element X from AH, and we'll prove that that is also an element of HA. Okay, so since X belongs to HA, and along with we choose A inverse, that is also from A inverse H. Okay, we choose A inverse from A inverse H. Obviously A inverse H is the coset containing A inverse, so A inverse is a member of A inverse H. So by this argument, we know that whenever X belongs to H, Y belongs to BH, then the product is in ABH. So obviously this X A inverse is a member of AH into A inverse H. Consequently, this is A inverse H, which is equal to EH, that is equal to H itself. What is the meaning of this? So if we start with X belongs to AH, then by making use of this A inverse, we can prove that X is a member of, okay, so this product X A inverse, not only this X A inverse is a member of H. Okay, that is X A inverse can be written as some small h belongs to H. So what is the meaning of this? X can be written as HA. Okay, HA is obviously a member of HA. So we start with X equal to H, then X belongs to H, then X belongs to HA, which shows that H is contained in HA. Similarly, the similar fashion you can prove that HA is contained in H. So using these two arguments, we can say that AH equal to HA rho A. Okay. So H is a normal subgroup. This is the definition of the normal subgroups. This H is a normal subgroup if we assume this operation is well defined. Okay. This is theorem 14.4. So this is this theorem, theorem 14.4. So if we make use of this, then you can easily prove theorem 14.1. So that is the first statement. We start with the phi is a homomorphism from G to G prime, and H is the kernel. As soon as we collect the kernel, this H satisfies H is equal to H. Then obviously the left coset multiplication is well defined using 14.4. That means set of all left cosets can be considered as a groupoid or a set together with this binary operation. Okay, so once you assume this binary operation, you can easily get the associative property, existence of identity, and inverse as well. That means if you consider this factor group is the set of all left cosets. Then if you collect that S is the set of all left cosets of the kernel. Here this H is the kernel. A belongs to G. Then assuming this H and BH, or by using 14.4, we can say that this is the binary operation. Then we can easily get AH BH CH. Okay, CH is same as A B C H. Okay, the similar fashion, this is same as you can see this AH BH HBH into CH is same as this ABCH. That means this is ABCH, both are same. So which gives the associativity in a set of all distinct left cosets of kernel. And if we consider EH, then EH AH is always AH, so that EH can be considered as the identity element in the left coset multiplications. And for any AH in S, we have A inverse H. Okay, such that AH A inverse H, when you operate both of these cosets, then we have A inverse H. Consequently, EH, that is equal to identity. So once you prove this is a binary operation, then you can easily say that this is a group. Okay, not only a binary operation, it satisfies the axioms of the group. So that group, if you consider H and left H is a normal subgroup, or H is a kernel, then you can easily define this group of distinct left cosets, and that group is called factor group. Okay, so that is the idea of the first part of 14.1. And the second part, this operation enable us to define a map mu from this S. Okay, S is the set of all distinct left coset to phi of capital G. Okay, so how will you define this function? This function is defined as mu of any coset. Once you write a coset, then we have A, then that coset is mapped to phi of A. Okay, so this is obviously a binary operation. Sorry, this is going to be a function, and this is a homomorphism as well, because mu of AH BH, by definition this is mu of HBH is ABH, obviously. Then AB is the image of this is phi of AB. Okay, then this is phi of A, phi of B, and phi of A is defined to be mu of AH, and phi of B is defined to be mu of BH. So which shows that mu is a homomorphism, and you can easily prove that this mu is 1 1 and onto as well. Okay, so in order to define this as a one function, we assume mu of h equal to 0. Okay, mu of h equals 0, then finally we will prove that h is also 0. 0 means h is the identity of that group. Okay, that is identity is eh itself. Okay, so we assume mu of a equal to 0, then phi of a equal to 0, because mu of h equal to mu of, not mu of a, mu of h equal to 0 means image of h under mu equal to 0. Image of h is defined to be phi of a, so phi of a is 0. Okay, so phi of a 0 means a is a member of the kernel phi, and kernel phi is defined to be h. Obviously, if you take an element a from h, then ah, the coset containing a is same as h. So whenever mu of h equals 0, then we will get h is equal to h itself. H means h. So this is a one function, and obviously this for every element phi of g, we can get an element a from g, and using that a we can define this coset h. So for any phi of a, there is h. So this phi, the mu is also a isomorphism. Okay, so this is what we discussed in or asserted in theorem 14.1. Moreover, if we continue this discussion in any subgroup h of g, such that h equal to ha, then this set of all factor group, we for the time being we denote that set as S, set of all h, a belongs to g, is a group. Okay, is a group under the binary operation defined above. Okay, so this group is called factor group, and that is denoted by g over h. This is g over h. This is denoted by a set of all distinct left cosets. Okay, this is always a group, and this group is called factor group. And it is read as g over h, not g by h. For the simplicity, we usually says g by h, but the actually this is read as g over h. That is the meaning of this.